Okay, folks, in this lecture I want to talk a little bit about the idea of histograms. So, if you remember from our video before class, a histogram in some sense is how we turn continuous data into a bar graph. We kind of just categorize all data between the endpoints of each bin. So here, we're saying that there are 3 elements that have values between 5 and 7. And remember the rule, if it is right on a boundary, the rule is to put it in the larger bin. Now, here we have some data, and this has to do with the weight of 30 oysters that were collected. And you'll find this on our Moodle page as well. You should see it under supplementary notes. You'll see this oyster data. And all we care about is the weight in grams. There's some other information here, the volume of it, and something about its picture coordinates, whatever that means. But for our purposes, we just care about the weight. So we have 30 elements here in our data set, and you can go onto Moodle and check that out yourself. So we have our 30 elements here. So n is 30. And, well, this is just a picture of the data system. I can't really scroll. But I can say that the minimum element is in row 19, has oyster ID 19. So, and that is 5.22. And you can check that the maximum value that we see in oyster weights is in oyster ID 3, which is 17.42. So we indeed have 30 data points here. So the number of bins we should have should be about the square root of that. Doesn't have to be exact, but it's going to be about square root 30, which is like, I don't know, 5.7 or something like that, somewhere between 5 and 6 anyway. So if we have 5 bins, that's good. If we have 6 bins, that's good. If we decide to have 7 bins, that's probably okay too. And we'll see examples if we have far fewer or far more than around this range, how it doesn't end up displaying our data in a nice way, in a way that's easily understandable. So the range of our data set is the largest, 17.42, minus the smallest, 5.22, which is 12.2. So there's a range between the largest and the smallest element of our data set of about 12.2. So Google made some choices here, and I think they're pretty appropriate choices. So I just got Google to make this histogram. I didn't specify too much here. But Google decided to have the boundaries of our bins as whole numbers. And that makes sense, especially in non-scientific capacities, since when people in the everyday public are reading numbers, they like to see round numbers. They can think about those a little bit easier. So Google said, well, the minimum's 5.2, so let's say our first bin starts at 5. And the only choice I didn't like that Google made is that this last bin, which has the same width as the other bins here, which all have width of 2, it decided to make the last bin have width a half, even though they drew it with the same width. So I don't really like that. I would rather make this 19. And then this bin width would be 2. And that's a reasonable choice. So if we round our minimum down to 5, so the rounded min, and rounded max, we'll go all the way up to 19 in this case, and I'll show you why I decided to do that. Then our range, with our new range, is 19 minus 5, which is 14. And 14 is divisible by 7. So we can have 7 different bins. Between 5 and 7, between 7 and 9, between 9 and 11, etc., all the way up from 17 to 19. So if we decide that the number of bins is 7, that's around square root 30. 5, 6, 7, something like that is a good choice. Then our bin width is going to be, well, it's our range, which is 14, divided by the number of bins, which indeed, as you can see below, is 2. So we can say that we have 30 data points, and this graph here shows us that, hey, there's kind of a nice trend going on here where the data seems to be centering around, I don't know, somewhere between 9 and 11, so that seems to be where most of the data is, and then it kind of spreads away from that a little bit. So I think this is a reasonable bin width and number of bins for this problem. And you can easily read off some information here. Let's say we wanted to know where the cutoff for the smallest 30% of our data was. So what is the smallest 30%? Well, we have 30 elements, and we're looking for how many of them are in the smallest 30%. So if we multiply that by 30%, or 0.3, we get 9. So we want to know the cutoff for the smallest 9 oysters in our data set. So if we look here, our histogram easily tells us that there are 3 oysters that have weights between 5 and 7 grams, 6 oysters that have weights between 7 and 9 grams. And you can see that here if we look at the top of the bar. It goes up to a height of 3, and the second bar goes up to a height of 6. So we know that the smallest 30% of our oysters, the smallest 9 oysters, are below 9 grams. So we can easily read off information from this histogram as well, which is really, really nice. Let's change some things about our histogram. Let's change the number of bins, and let's just see what happens. Bin. So here's a histogram of the same data set, but now we have a bin width of 3 instead of 2. So, and again, I don't like what Google does here, where they have the same bin width, but they don't have a good end bound. Since the bin widths have to be consistent, we want to make this go all the way up to 20. So same idea. Now we have 1, 2, 3, 4, 5 bins. We kind of rounded to say our min was 5 and our max was 20. So our range is 20 minus 5, 15. There's 15 grams between our largest 20 gram and our smallest 5 gram. That's when we round. That's our rounded min and max. And if we want to have a bin width of 3, we know that 15 divided by 5 is 3. So we have 5 bins, and each bin has bin width 3. And you can see this isn't too bad of a histogram. I kind of like the one previous. I think that shows a little more what's going on, but you still get this nice shape to the data. You can kind of still see that it's centering around somewhere in this bin between 8 and 11, and it's falling off on either side. So most of our data is somewhere centered around something between 8 and 11, and there's less and less data as we get farther away from that kind of largest bin. Let's see what happens in more extreme situations when we have very few bins and too many bins. So here's another situation where we have 3 bins. And here you don't get a lot of good information. And again, just to keep everything consistent, we have a bin width of 5. So I want to make the last bin width have 5 as well. That's just a little something that Google does that really isn't the best practice. Anyway, here you can see we have too few bins, and we really can't get a feel for what's happening. We know there's lots in here between 10 and 15. There's quite a few between 5 and 10, but not as many. And then not too many between 15 and 20. But we lose some fidelity there. We can't really see the shape of the data. And I think you guys will agree it's a little more clear what the story is in the previous bins, especially that first histogram that we looked at. So this one has too few bins. 3 is too far away from the square root of 30 to be useful to us. Let's go extreme in the other direction. Let's have too many bins, and let's look what happens there. So here we have bins of size 1/2 of a gram. So this goes all the way up from 5 to 1750. I don't even know how many bins we have here, but it's far too many. It's something like probably 20 bins or something like that. And you can see that we don't really get a picture of what's happening in the data set too much, since most of our bins just have one element in them. So it's almost like an ordered list of data. It's like you just ordered this data and didn't draw a picture. So it's not as instructive here. You don't really see too much of the shape of the data. And the moral of the story, of course, is just to make sure that you have your bin width selected appropriately. Anywhere around the square root of the number of data points you have is appropriate. And you can fudge the min and fudge the max to make your bin widths work out fairly well, as long as you don't fudge too egregiously. And you also do have some choice in selecting your number of bins. If you're really concerned about having round numbers here, then you want to make sure that you're picking some number that divides evenly into the range of the data, which again, you can fudge a little bit to suit your purposes. So you have a lot of control here. There's no hard and fast rules for making histograms. You have to use a little bit of your judgment. Okay, so I want to do one more example of a two-way bar chart here. And this is comes from exercise 2.22 in your textbook. So if you want to see exactly how it's worded, you can check out that exercise in McClave and Sinchich Statistics 13th edition. But let me tell you, at least in words, what's happening here. A researcher that was researching sports decided to determine the way goalkeepers in soccer jump when they're defending penalty kicks, when either their team is behind in score, the score is tied, or they are ahead. And if you've seen penalty kicks in soccer, if you haven't, maybe go and Google one or watch one on YouTube. But when a penalty is kicked, the goaltender will either dive to the left, dive to the right, or stay in the middle. And the whole idea is they want to kind of guess or read the way that they think the kicker is kicking the ball into the net. And the researcher determined that when the goalkeeper's team was behind in score, that they dove to the left 29% of the time, they never stayed in the middle, and they dove to the right 71% of the time. When the score was tied, it was 48 to the left, 3 in the middle, 49% to the right. And when they were ahead in score, it was 51% to the left, 1% to the middle, and 48% to the right. So with these two-way bar graphs, you can group them by either category. So you can group them by score category, or you can group it by the category of the way that the goalkeeper jumped. So then it really depends on what you want to get across to your audience, which is the best way to group. So if we group by score category, then this is what our two-way bar graph will look like. You can see in the behind category, here is the bar for left. That goes all the way up to 29%. They didn't stay in the middle, so there's no bar in the middle. And they went to the right 71% of the time, which is somewhere around here. When the score is tied, 48 to the left, 49 to the right, 3 in the middle. So here's 48 to the left, 49 to the right, 3 in the middle. And you can see this is 50 here. So it's just below 50% on each of these bars. And ahead, 51, 1, 48, 51, 1, 48. Of course, this isn't super accurate. This is just me drawing freehand, but hopefully you get the right idea here. So this is what it looks like when grouped by score category. And now we'll draw it grouped by direction category, left, middle, and right. And we'll have separate bars in each of these categories for whether they're behind, tied, or ahead. So we'll see what it looks like there. So using the colors from the previous slide, behind was, for example, circled in this brown color, so that's the brown bar. Tied was gray, and ahead was purple. So using those colors, this is what it looks like when you group by direction, by left, middle, and right. And what do you want to glean from this? So a good question is, what can you tell about the data from each grouping? Maybe from this grouping, it looks like they dive to the left quite often, they dive to the right quite often, but they rarely stay in the middle. So maybe for this grouping, a reasonable conclusion that you could draw, and that this bar chart highlights, is that goalkeepers rarely stay in the middle. If we look at the other chart again, you can pause the video and go back to it. If you group by score, then a conclusion you may read, so in the other one, so in the first chart, on the previous slide, maybe a reasonable conclusion that you could reach there is goalkeepers tend to dive to the right, more so only when their team is behind. But again, you could read either conclusion from either graph, but in my opinion, the first chart shows this a little more easily, and our second chart shows this a little more easily. But it is all up to the person making the graphs how they want to set it up to show the story of the data that they want to show. And next day we'll continue on with the idea of descriptive statistics as well.